Over the last few classes, we have done simulations on several case studies, including gender discrimination, opportunity cost, CPR, and the medical consultant studies. Now, suppose that we had done 10,000 simulations for each study. Right. The graphs you see on this screen show the null distribution for each of those 4 case studies. Opportunity cost in the upper left, CPR in the upper right, medical consultant study in the lower left, and the toppers and listeners study in the lower right. Look at these graphs. You might notice there's this common shape that shows up. All 4 of these have this unimodal, symmetric, bell-shaped curve. And that's not really coincidence. It's also not coincidence that the medical consultant study here in the lower left is the worst of the bunch. I'll get back to that in a moment. But it is common for distributions in general to be skewed or contain outliers. When you're first starting out, the original sample, not uncommon for it to be skewed. However, the null distributions we've so far encountered have all looked somewhat similar and, for the most part, symmetric. They all resemble the normal distribution, and that's not really coincidence, but rather is guaranteed by the central limit theorem. The central limit theorem guarantees that a sample proportion or a difference in sample proportions will follow something that resembles a normal distribution when certain conditions are met. These conditions will always fall into 2 categories: independent observations and sample size. So what I mean by independent observations is that the results from one observation in your sample has nothing to do with any other observation in your sample. What it means for us, we can assume independence when either the sample was randomly selected from less than 10% of the population, or observations were randomly assigned to treatment or control groups. Either way, the key word here is random. Our sample needs to be random, either by selection or by assignment. The other condition is sample size, and that basically goes with larger samples tend to be more accurate than smaller samples. So to be reasonably certain of a unimodal symmetric distribution, the sample should be at least a minimum sample size. Though what qualifies as minimum will differ from one context to the next. But I'll give you some suitable guidelines in some later lessons. For right now, I'll just kind of show that sample size. Suppose the true population proportion was 95%. The probability of success was 0.95. That basically corresponds to that 19 out of every 20 times you do something. The figure here shows the distribution of a sample proportion when the samples were 20, 100, and 500. So what is each point, each observation the sample represents? And describe how the distribution of the sample proportion changes as the sample gets larger and larger as we go from one to the next. Well, in this first graph, each dot of this graph represents a sample of 20. And where we do a sample 20, find the proportion. Then we do a different sample of 20, find another proportion, and do another sample of 20, do another sample proportion, and so on. The middle graph, the dots represent samples of 100. So you do something 100 times, you find that proportion of success, do it again, find that proportion of success, and keep doing it until you build up this dot plot. The last one is where you do samples of 500. Okay. Again, where you do a sample 500, find the proportion, another sample 500, find the proportion, and so on. Now you might notice the very first one, the sample size 20, you can see that this graph looks nothing like a normal distribution. In fact, if I try to fit one on, it doesn't fit at all. What that tells me is that the sample of 20 is just too small for the central limit theorem. So a normal distribution is not a good fit here. The middle graph better, but you kind of notice there's this whole, this left tail is kind of much longer than the right tail, so there is a bit of skewness. Normal distribution kind of fits, not terrible, but you can see this whole left is a little bit off. So in this case, I'm kind of borderline, but I'll say that it's better, but samples of size 100, and it's still a bit too small. For samples of 500, you can see a normal distribution fits right on top of it. Looks pretty nice. Fits pretty well. So samples of 500, definitely large enough. You can probably get by with less than 500, but that definitely guarantees that the sample is large enough.